Hello everyone. Let's have a quick review on heat and work, because in studying thermodynamics, heat and work concept play an important role. In mechanics, work involves a transfer of energy. But unlike heat, work is energy transfer where temperature plays no role. Whereas heat, it involves temperature difference. And another thing to note is that a body can generate unlimited heat. Thus, heat is not something which a body contains a definite amount. Or in other words, heat is not a property of the body. And Joule did some experimentations and came up with the mechanical equivalent of heat. Similar process that you have done in your activity 6, where the accepted value for this ratio of the amount of heat generated to the work done is equal to 4.18 joule per calorie. So in equation form, this is W over Q. That's equal to mechanical equivalent of heat. Let's try a sample problem. And here we have a 200 gram copper calorimeter, contains 400 gram of water at 30 degrees Celsius. It is steered by paddles, rotated by applying a torque of 0.05 joules, the paddle being rotated at 120 revolutions per minute. Then calculate the rise in temperature of the water per minute. So rise in temperature. So from the given problem, we have the mass of the calorimeter given 200 grams and the mass of the water equal to 400 grams. And we know the constant in our previous topics. We know that copper has a specific heat equal to 0.093 calorie per gram Celsius degree. And for the water, we have specific heat of water is equal to 1 calorie per gram Celsius degree. And torque is also given. Torque is equal to 0.05 joules. And the frequency of revolutions, we have 120 revolutions in a minute. So what is being asked is our delta T. But we can solve the delta T if we can solve the Q, the heat transferred or absorbed, or the interplay between this mixture. Using calorimetry, we have Q is equal to MC delta T. And in here, our mass involves two masses, so we have mass of the calorimeter, C of the calorimeter, plus the mass of the water and C of the water, all with the same change in temperature. But since we do not have Q in here, since our delta T is our unknown, we cannot use this equation to solve for delta T. But we can use the mechanical equivalent of heat, J is equal to W over Q, and we already have the value for J. If we have the J and work, we can solve for Q. And then we can solve for W in this case, since W is equal to the torque times the angular displacement in radians, basing our previous lessons in mechanics. So torque is equal to 0.05 joule, and our angular displacement in radians is simply equal to 2 pi and revolution. So this is equal to, what's the value for work? 37.68 joule of work. This is per minute. Okay? So having the value of W, we can solve for Q. Q therefore is equal to W over J, and this is equal to 37.68 joule over 4.18 joule per calorie. Therefore, canceling joules, we have 9 calories. So, this can be substituted to our value in here, our equation in here. So, substituting to our equation, we have 9 calories, and then this is equal to 200 grams times 0.093 calories per gram Celsius degree, and plus 400 grams times 1 calorie per gram Celsius degree, all delta T, the same change in temperature. So this is equal to 9 calorie equal to, calculating this, Q 418.6 calorie per Celsius degree, since gram already cancelled out. So, and all delta T. So therefore our delta T is just equal to 9 calorie over calories over 418.6 calorie per Celsius degree, and cancelling calories, we have 0.021 Celsius degree. This is our answer. The example shows that we could put an infinite amount of work into the body without changing the condition of the body. So example, we can generate an amount of heat by rubbing our hands together without changing our hands condition. So thus heat and or work in a body or property of a body is meaningless. So what's the idea? The heat transfer and the work done depends on the process. And this is called the thermodynamic process, defined as the interplay of heat and work in a system as it changed from the initial equilibrium state to the final equilibrium state by interacting with other objects. So, heat and work depend on the state of the system. Now, as it changed from initial state to its final equilibrium state. So, from this illustration, consider a portion of matter. Okay, sample, this is our system. Isolated. So we call this isolated matter as our thermodynamic system. Everything that's around having a relation or affecting our system is called the environment. And then the Q and W are not characteristic of the equilibrium state of our system, right? But the process of interaction between the system and environment involves Q and W. So Q is the heat transferred to our system. So let's label this as positive. And also, it is the heat transferred from, and let's label this as negative. And also the work done on or by the system. So this is the work done on the system, and let's label this as negative. And the work done by the system, let's label this as positive work. Work done on the system is negative. Work done by the system is positive. Whereas our Q, if it is generated or transferred from the body, Q transferred to the body is positive, but the Q transferred from the body is negative. We can have a sample illustration in this thermodynamic process. Okay. In here, we have a gas container with a movable piston as our system. So this is our movable piston. Okay. The initial state I has the pressure Pi and the volume Vi. So the heat is being transferred from the environment to our system Q by means of a sample, a Bunsen burner. And the work done is by compressing, okay, moving down of the piston, or expanding, moving up of our piston. If the gas expands, then it's the work done by the system. And if it compresses, then that's the work done on the system. So this is negative, this is positive. And our heat is positive Q. Note that work done on the system if compression happens, and work done by the system if it expands. Okay. So our final equilibrium state has PF and VF. So the work done by the system in displacing the piston through an infinitesimal distance ds is equal to dW equal to F dot ds. But since our F for a constant pressure is just equal to PA, so our equation becomes PA ds. But then ADS is just equal to the infinitesimal volume change. So this is dV. So dV is the differential change in the volume of the gas. That's the total work done by expanding from an initial volume VI to the final volume VF. Or the total work in equation is equal to dW, or the integral of P dV from initial to the final volume. Or this reduces to P, the change in volume, or P volume final minus volume initial. This equation for work is applicable for constant pressure process. Graphically, the total work is represented by the area under the curve in a PV diagram. So we have in here the state of the system represented by the point. This is our initial state, initial equilibrium state I, and the final equilibrium state F. The area under the curve is the work done. Work is equal to the area under the curve. And there are different ways in which the system can be brought from initial to the final state. So let's have this illustration. So the work depends on the initial state and the final state, as well as the thermodynamic process or path taken. So depending on the path taken. If we consider the path thermodynamic path IAF, we have in here from I to A, we have a constant pressure process. And then from A to F, we have a constant volume process. But taking another path from I to F, we can also have IB F path, wherein IB is a constant volume process. BF gives a constant pressure process. But the same initial and final state. We can also choose IF directly or IF path. In this case, both pressure and volume are changing. Take note, all of this path given become a complete thermodynamic process from initial equilibrium state to our final equilibrium state. So different paths correspond to different works done. In here, we have the greater work or the greatest work done is from IAF path, because work is the area under the curve, then work greatest in this path. And the least would be in path IBF. In our next lecture video, let's consider the first law of thermodynamics.